Okay, it looks like it's time to start, so I will. So I want to talk about lattice gas models where we have repulsive interactions between the lithium atoms. And what happens in that case is usually the atoms don't remain randomly positioned in spite of the interaction like has been happening up till now. So there are some exceptions to this, which we'll talk about later. Just giving you an example here where there's a very strong voltage drop as the lithium goes into this cubic titanium sulfide. Now that means there's a repulsive interaction between the lithium atoms, but mean field theory fits the curve fairly well. So this is not typical. Okay, so I'm going to go to my document camera and just talk about, you know, what the issues are here for some period of time. So I think you should see my document camera now. Is that right?
Yeah.
Okay. So here's the situation. We'll talk about the typical triangular lattice of sites that we have in NMC or NCA or LCO, all these types of materials. And we're going to assume that lithium atoms don't like to be on the nearest neighbor sites. So of course, lithium atoms come from the outside, they diffuse along the layer, and they park themselves somewhere. So let's say there's one here, right? So another lithium atom comes along, and it is not going to want to go in these near neighbor sites around the filled one because it's a very repulsive situation. So it will go somewhere else. Maybe it'll go here. And then another one will come along and it'll say, you know, I don't want to go on a near neighbor site either. I will go here, perhaps. And another one would come along and it might say, you know, I don't want to be on any near neighbors of these, and it'll go here, for example. All right. So the question is, how far can you fill up this lattice? What fraction of sites can you fill up this lattice and avoid these near neighbor interactions altogether? And the answer is you can fill up to 1/3 of the sites if you put the lithium atoms on particular positions. So this one that we put here, this is a poor choice because it means we can't pack any lithium into any of these positions. If we do, we put a near neighbor interaction in place. So I'm going to redraw this and show you the way that they will arrange themselves to give the maximum filling. All right. So I'll draw another lattice down below. I don't know if you folks have got, you know, this nice paper for drawing these things. Maybe somebody can let Eric in. Thanks. So you have your triangular lattice of sites, and then if you want to fill up to the maximum composition at x equal 1/3, you'll fill up like this. Okay. And someone, I think it was David, emailed me a question. He said, you know, what is a superlattice? Or maybe it was Zach. Can't remember who. You know, so if you look at this lattice of sites, you know, we said it had unit vectors that describe it of the same length. Well, now you have an expanded repeating cell because there's lithiums not on every site. The periodicity's been increased. So the new unit cell I'll draw in blue it would look like that. And this is what we mean by a superlattice. It's a larger lattice that exists on top of the existing one. So the point is that if you arrange lithiums like this, you can avoid all nearest neighbor interactions. And the problem comes when you add the next lithium atom. You know, if you want to keep adding lithium, at some point you have to put one somewhere. So say you put it here in red, and then you pay 1, 2, 3 near neighbor interactions, okay? So when you have repulsive interactions, the lithiums try to avoid them as much as they can at the beginning. All right, so let's just talk now. I'm going to remove this piece of paper and put another piece of paper on. I hope that's okay for you. I'll send you these pieces of paper, or whatever they're worth, at the end of this class. So what happens if you have a strong second neighbor interaction? Well, what happens then is you draw your lattice of sites again. And you put a lithium atom somewhere, so maybe here, and then you say, okay, there's a strong second neighbor and also a strong first. So you don't want to fill the first neighbor sites here, and the second neighbor's there. You don't want to fill that. So the lithium will go in the third neighbor. So this is the first neighbor of this one, and this is the second neighbor of this one. This is the third. And then if you fill up to the maximum there, you'll figure out that you fill up every 1 in every 4 available sites. So you fill up to x equals 1/4. So there are all these compositions where the lithium can arrange itself to avoid interactions. And they turn out to be 1/3, which means avoid first neighbor, 1/4, avoid first and second neighbor, 1/7, avoid first, second, and third neighbor, ... Okay. So this is what can happen. And the question is, what is the consequence of this ordering that takes place on the voltage curve? What happens? Okay. What happens to the voltage versus lithium content curve when this ordering takes place? So before I go to that topic, maybe there might be some questions about this. So I'll just pause. Okay, so hearing no questions, I'll go along. So what I want to do now is calculate the T equals 0, so 0 temperature voltage curve for the case where you have a site energy for E0 and the first neighbor interaction U1 greater than 0 so repulsive, and U2, U3, dot, dot, all of them equal to 0. So we only have first neighbor interactions. That's it, okay? That's it. So let's go ahead and try to do this. So again, we write down our triangular lattice of sites. I think I've got that okay. Need another row, I guess. Did something wrong. There we go. Okay, so then what we do is we say, we know that what we're trying to do is arrange the lithium in such a way to minimize the free energy. So if we put lithium on near neighbor sites, that creates a positive or repulsive interaction that raises the free energy. So we're going to avoid doing that. So for 0 less than or equal to x less than or equal to 1/3, we can completely avoid near neighbor sites like I showed you. Okay? And for that case, we'll put the lithium on there. I'll use x's for where the lithium's going to go, up to x equals 1/3. We'll completely avoid near neighbor sites and fill up the lattice like that. Okay? And we can write down an expression for the internal energy or the free energy. So remember that G equals U minus TS plus the pressure times the volume. We neglect that term because it's small, and we're doing it for T equals 0, so this term goes away. So the internal energy and the free energy are the same in this case. So G will be just equal to the number of sites that are filled multiplied by the site energy, the energy that you get when the lithium falls into the site. So it's just minus E0 times N. So N is the number of sites filled. So this is minus E0 big N times X. So that means G over N equals minus E0 times X. And you can calculate the chemical potential and hence the voltage, because the chemical potential is the derivative dG by dN. So dG by dN is just minus E naught and the voltage, this is the chemical potential, and the voltage is the negative of this. So the voltage for X between 0 and 1/3 will just be equal to E naught. Okay, so that's very simple. So now let's see what happens when we put on some more lithium atoms. So now we'll work between for 1/3 less than or equal to x less than or equal to 2/3. So now what we're going to do is we have to say, okay, let's put a lithium atom somewhere. We'll put it here. I'll use a black square. That creates 3 near neighbor interactions. There's no way we can avoid it. If we were to put a lithium atom here, we would create 4 near neighbor interactions. 1, 2, 3, 4. This is not a good place to put the lithium. The best place is to put them on another of these superlattices where you only create for every one that you add 3 near neighbor interactions. Is that clear? Is that unclear? Is there anyone on this call?
We're here.
Well, yes, we're watching.
Okay. Sounds like somebody's in the ocean there. Okay, so now we want to write down the free energy again for this range of x. So you've got a certain number of sites that are filled. Just like before. And then you have some interactions. Okay, so I've drawn the situation with, you know, the second sublattice, the black one, completely filled. But let's just see what happens when we put the first atom in there. We have to pay an energy cost of 1, 2, 3 U1. So there's a term 3 U1. And what do we put here for the lithium content? We've already filled up 1/3 of the sites. So if we put another lithium in, this term is x minus 1/3. If you think about this, if x is equal to 1/3, you haven't filled any of these black squares at all. If x is equal to 2/3, then you've filled up all of these black squares. And how many interactions would you get? If you drew them all in, you would find there's 1 for every available site. And then this is multiplied by n because there's n sites on the lattice. I'm trying to think if there's a better way to explain this.
Hi, Jeff.
Yeah.
For this, so it looks like you average, because this is just when filled up to 1/3, then you add 1 more, right? And in this case, the nearest neighbor interaction is unavoidable. And so, how would you convert the three interaction convert to 1? It is because you for each you average the 3 interaction to all the sides. That's why it becomes 1. Is this the
No,
reason?
if we draw them in, all of them, I don't want to do that because I'll ruin my diagram. But if you draw in all the near neighbor interactions that take place when you have filled all these black ones, you will find out that there's one of these bars labeled U1, an equal number of these bars compared to the total number of sites on the lattice.
I see, because some of the interaction is repeated when you count. So
yeah, some of them are repeated when you count, and also there's a lot of them that are not. There are missing interactions because there's no lithium on this site, which is going to be red in a minute.
I see. Okay, thank you.
Okay, so anyway, if you then want to get the chemical potential and hence the voltage, you take the derivative of this. So 1 over n dg dx, which is the same as dg dn. And that turns out to be equal to minus E naught plus 3U1. So the voltage equals E naught minus 3U1 for 1/3 less than x less than 2/3. Now, this is really very intuitive when it comes out and you look at it like this, because when you put a lithium on the black square, you pay 3U1. The voltage drops by 3U1 compared to what it was when you weren't having to pay those 3 near neighbor interactions. So now let's go further. I'll change to red. You'll have to tell me if you can see the red ink or not. Is that okay, or is that too pale?
That works.
That's good.
Okay. Okay, so now we're going to fill up more. And that means, where are we going to put them? Well, we're going to put them on these empty sites. We have to. And when you put a triangle there, there's 6 neighbor interactions that are created here. So if you write down an expression for G again, now it's the value of the free energy that existed when you were 2/3 filled, plus this additional part that you get. So what we have to do is take the value of the free energy when x is 2/3. It has to be continuous, so we put 2/3 in here, and now it's going to be minus E naught n x. That term is the same. And then we have to account for the fact that when we fill up to 1/3, we have no interactions. We fill up to 2/3, we get this, put the value of x equal 2/3 in there, which is going to be U1 times n. And now, every additional lithium that we add creates 6 near neighbor interactions. So it's going to be 6U1, and now it's x minus 2/3 times n. And if you then take 1 over n dg by dx which is dG by d little n, which is the chemical potential, you get minus E naught plus 6 U1. So the voltage as a function of x is E naught minus 6 U1 in this range of composition. And again, it's very intuitive because for every lithium that you put into one of these sites, 6 near neighbor interactions have to be paid. So I want to sketch this voltage curve. And I obviously can't do it on this piece of paper. So I'll go to a new piece of paper. So what does the voltage composition curve look like? So you have some site energy which sets the voltage at the beginning, and it goes along flat. And then at x equals a third, it drops by a value of 3 U1. And then it's constant again. And at 2/3, it drops again by a further value of 3 U1. So the total drop is 6 U1. So this is the signature of ordered compositions in a voltage composition curve. When you see steps in the voltage versus composition profile, it is often a hint that there's ordering of lithium going on. And you expect the steps, this is a step, the steps at ordered compositions. Okay, so does that make sense to people? It's hard in a online class, to sort of poll the class. Maybe I think there is some poll thing in Teams that I could use, but does this make sense?
Hi Jeff, this makes sense, but this model just applied to the layered structures where the lithium can freely distribute on 2 dimensions. For the LFP materials where there are channels, I guess its model does not apply, right?
Well, also in LFP, the net interaction is attractive, so you don't see this type of thing. But there are nice situations where the lithium goes in tunnels and there is a repulsive interaction, and you see this. You see these steps. A good example is molybdenum dioxide, and then you see a nice step at 50% filling, where every second site along the tunnel becomes filled. You see a nice step at x equals a half.
Okay, thank you, Jeff.
Thanks for the questions, Wentao. It's awesome. I wish some of the graduate students were so curious as you are. Okay, so anyway, let's think about what happens to the differential capacity here. So here you see the rate of change of voltage with composition is incredibly large. dV by dx is large. So therefore, the differential capacity, we talk about dq by dV in our battery measurements, but the charge is proportional to the lithium composition. So dq dV is proportional to dx dV, and dx dV will be 0 or very small at an ordered composition. dx dV is small at an ordered composition. All right. So I want to go back to the PowerPoint for a minute and just talk about a few things. Okay, I think you should see the PowerPoint now, right?
Yes.
Thank you. Okay, so here is what these three interpenetrating sub or super lattices look like on the two-dimensional triangular lattice gas. So this is a figure from McKinnon's thesis, and what I'm doing here is coming more or less right from his thesis for the zero temperature case. So there was this paper, 1978. So Arthur Thompson worked in the same research group as Stan Whittingham, our Nobel Prize winner, okay, just down the hall from each other. And it's very strange that Whittingham is not a co-author on this paper. I don't know quite why. But anyway, what he says here, a new electrochemical measurement applied to the lithium TiS2 cell reveals subtle changes in the slope of the voltage composition relationship. These anomalies occur at compositions where ordered structures among intercalated lithium are predicted for lattice gas theories. Lithium TiS2 appears to be a nearly ideal model for the study of composition and temperature-dependent properties of the two-dimensional lattice gas. Okay, so that's a great abstract, and you would say, yeah, physical review letters. What a, in those days, science existed, nature existed, and physical review letters, and those were the big journals. There was no advanced functional materials, nature communications, all this other stuff. So you want to publish in a high impact journal, it was Science, Nature, or physical review letters, basically. So this is in one of the most highest impact journals around. So here we go. He says, one set of such super lattices occurs when all near neighbor lithiums are equidistant. On a two-dimensional triangular lattice, equidistant structures can appear when x equals 1. That means every site is filled. 1/3, we took a look and we saw the ordered state at 1/3. 1/4, that's when you avoid first neighbor and second neighbor sites. 1/3 is when you avoid first neighbor sites. So we drew this ordered structure for 1/4, and then there's other places where they occur too. Okay, as discussed by Cabaorgi and Kanamori and Cabaorgi. The ordered structures one expects to see on any lattice will depend in detail on the interactions. So he shows you here at 1/4 and 1/9 where there's features in dx dV, right? And he shows you on the voltage curve there's a flat spot at 1/4. And he claimed in his paper that this corresponds to ordered compositions of lithium. So what's wrong with his interpretation?
Where's the 1/3?
Well, there isn't any ordered structure at 1/3 in this stuff. But wait a second. Are you happy with what he's saying here? Okay. Well, it's a failure of education, which is the story of my life. So we're going to go back to the document camera and look at what we just did. Okay. So remember this. Remember very clearly what happens at DXDV at the ordered state, right? Okay. So now we're going to go back to the document camera. You should see the document camera, right?
Yes.
Okay, where's the ordered state? What happens at an ordered state? Do you see a big voltage drop or do you see a plateau? And what do you see in differential capacity? Do you see a peak or do you see a small minimum at an ordered composition?
Should go through a minimum.
Should be a minimum at an ordered composition. Let's go back to the document, to the PowerPoint. Where is it? Here. There we are, right? So he claims there's an ordered composition at a quarter, but there's not a minimum. It's a maximum. So this paper in physical review letters can be proved to be wrong with kindergarten level arguments. What do you think of that?
That might be why his friend's name wasn't on the paper.
Maybe, I don't know. Okay, so what do we expect to happen? Okay, so this paper of Thompson's came out while I was a graduate student at University of British Columbia. And we read it in our research group and we all went bananas. We said, this is total bullshit, you know? So some of the theorists in the department, John Berlinski and Bill Unruh, did some calculations using Monte Carlo methods and renormalization group methods to figure out exactly what would happen on the triangular lattice with near neighbor interactions. So this is the voltage curve that they calculated. If you have near neighbor interactions, sure enough, look at 1/3, there's a giant step down. This is not at zero temperature anymore. So that's why things aren't completely flat. Okay, so sure enough, there's a giant step down at 1/3 and at 2/3, a huge minimum in the DXDV curve, right? Very, very clear. Thompson has to be completely crazy. So Bill and John and my supervisor, Rudy Herring and Ross McKinnon, submitted this paper where they said, okay, Thompson's a fool, to physical review letters, which is where Thompson's paper was accepted, right? Well, it was rejected. And it was rejected because it wouldn't be of sufficient interest to the readership. So it was eventually published in a journal called Solid State Communications. I think it still exists, but its impact factor is probably about 0.5 or something like that. I don't know. But the thing is, people cited Thompson's paper for years, saying, okay, this is what you get when you have lithium ordering. And it just means people don't think. They don't think about what they're doing. They just say, oh, it's in the journal, it must be right, blah, blah, blah. Okay, so that's just a little story for you. So I just want to gather my thoughts and see where I'm going next, so just hang on a second. Okay, so you should be thinking to yourself, okay, fine, Jeff. Lithium ordering doesn't cause this structure. Well, what the heck does? It's not lithium ordering. What does cause this structure? So I'll explain that probably in about 3 lectures from now. We'll learn where this comes from. But for now, we just learned that it's not due to in-plane ordering of the lithium atoms on the triangular lattice, all right? So then you have to ask the question, do any systems actually show this ordering that we are talking about here, or is it just a you know, a fiction? So let's take a look here. So this is from a paper that Ross McKinnon and I published way back in 1984. This is basically the same type of data as Arthur Thomson measured. So this is the voltage versus composition on the top panel and differential capacity versus composition on the lower panel for titanium sulfide cell, okay? And like Thomson, we see these humps at the beginning and sort of flat spots in the voltage curve in the differential capacity. And over on the right-hand side, this is for tantalum disulfide. Has basically the same structure as titanium sulfide, it just has tantalum instead of sulfur. And you see a very different looking set of curves. They have these humpy things at the beginning, these 2 humps, you know, 1 hump, 2 hump, 1 hump, 2 hump. But then look, at a third, there's a minimum. And at 2/3, there's a minimum. So A and B correspond to a charge as A and B is a discharge. And B's been offset from A just for clarity. And you can see in the voltage curve, there's a bit of a step down at a third and a bit of a step down at 2/3, right? So what do you think's going on?
Does this have something to do with the TA because it's different? The property is different from titanium?
Yes, it has something to do with the differences between the 2 materials. Okay, so we'll talk about that now. I'm going to go to my document camera again. So how do I do that? I think you should see the document camera, is that right?
No, it's still on the slideshow.
Really? Okay. How about now?
Yep, all good now.
Okay, good. Okay, so TiS2 is called a semi-metal. It means that the electron density at the Fermi level is very, very small. It's not a semiconductor where there's a band gap, and it's not a metal where there's a large electron density at the Fermi level. So it means there's very few electrons for screening. On the other hand, tantalum disulfide is a metal. And in fact, intercalated tantalum disulfide with lithium is a superconductor. My brother Doug wrote a PhD thesis on the properties of intercalated tantalum and niobium disulfide, which are superconductors. So very large number of electrons, lots of electrons for screening. So what does this mean? It means in TIS2, there's very poor screening. So it means the near neighbor interaction, the next near neighbor interaction, and so on. I should call these U1, U2, U3. They're all appreciable. And what that means is it's a very long-range interaction, so it's almost like mean field theory. There's going to be no reason for ordering to take place. I think I'll draw a sketch in a minute to sort of show how that works. But in tantalum sulfide, because the screening is good, U1 is, greater than 0, and then U2, U3 are all small. So this means the lithiums will really try to avoid the near neighbor interaction. And when they do that, they won't pay any penalty by, having second and third neighbors. Let me draw you what I mean. Right. So you put a lithium atom here, and you have a strong first neighbor interaction, you try to avoid these interactions. But if you also have a strong second neighbor interaction, and you were to put a lithium on the second neighbor site, if that interaction is just about the same as the first neighbor interaction, well, then there's no difference putting the lithium in the second neighbor or the first neighbor. So if these interactions are all appreciable, it's going to drive you to a random configuration of the lithiums. Whereas if the second neighbor is very small, then there's a good reason to put the lithium here, because you avoid all these first neighbors and you don't pay anything for a second neighbor, right? So this is the understanding about the difference between these two structures, two materials, just in hand-waving terms. Tantalum sulfide just is way more, the screening length is much, much shorter. So the interactions between lithiums are only felt over a small distance. Okay, any questions about that?
Does this change other properties of the metal? So for example, the oxidation states, would those be more ordered in tantalum disulfide rather than titanium, so that you'd have like alternating or repeating oxidation states?
I think in these materials, especially in tantalum sulfide, the electrons are fully delocalized. So I don't know whether the valence electrons, are very delocalized. So I don't think it makes sense to talk of titanium 4+ and titanium 3+ in a system like that. In TIS2, maybe you could see some local differences between the 3+ and 4+ on the adjacent sites. I don't really know. I don't think people have studied that very much in these materials because they didn't ever become commercially relevant and subject to a lot of study. It's unlike the layered oxides, where people do a lot of X-ray absorption spectroscopy to try to learn what's happening to the oxidation states of the transition metals as the lithium goes in and out. But I'm surprised Devia hasn't asked a question here about, you know, these are layered systems, and the lithium goes in, it should sort of prop open the layers. So why don't you have a strain-mediated attractive interaction in these things? Or do you? So that's something for you all to think about. Think about what it might cause, and we'll come back to this this topic next day. I see I'm pretty much done this particular set of notes. There's just one more thing I want to talk about before we move on to the next topic. So I'll send you the notes for the next topic either today or tomorrow. And since we finished this little section, I'll be sending you another homework as well. And I'll see you on Friday. Any final questions before we say goodbye?